Right. Now I think sometimes this connection is a problem. It's okay. And today we'll discuss some heat need for heat essay question discussion. So we'll discuss heat essay question discussion. Right. And can someone share the Pesuru heat essay question PDF in the group? Can you share? Past paper discussion need for heat. So this month we have to do the sessions as much as possible, and we want to cover lots of questions. So you should do the questions as much as possible. That is the target, right? So every night 10 p.m. Yes, we are tired, but only for this last 3 months we'll plan this. Unit 4, and I will share the this month plan. I will share definitely tomorrow. Essay question discussion, right? Okay, right. Hmm. Time is 10, 10, 10. Right. I'll share the PDF in the group. If I share the PDF, uh, right. Okay. If you're noticing any connection issue, please tell me. Okay. Now, no issue. Everything is fine. Right. Now, take the PDF, share in the group. The PDF, share in the group. Then we'll start. So don't worry, we'll do all the questions. Right. Okay. Right. Right. So we'll go to 2012 A level question. 2012 A level question. Essay question. And we'll try maximum to do at least 2 essay questions today. If it is possible, we'll plan to do 3 essay questions per session. But I think it's not easy as we think, but we'll give a small try. Right. 2012 A level. Consider a pond of cross section 2 meters into 2 meters and containing pure water, constantly being exposed to direct sunlight. See figure 1. See figure 1. The amount of solar heat radiation falling on the pond is 1000 watts per meter square. And assume that it is constant for the calculation below. It is constant for the calculation below. Now what they are telling there is a pond. That pond is filled with pure water. And cross-sectional area of the pond is 2 meters into 2 meters. If I do that for our understanding, 2012 A-level heat. When you read every sentence, clarify, understand every sentence. Without understanding of sentence, don't read the next sentence. Then only you won't be able to understand the question. Right? Okay. Then there's a pond. The side view of the pond, they have given in the figure. Side view of the pond, they have given in the figure. It's like this. This is the side view of the pond. We'll calmly understand these essay questions. Right? This is the pond. Side view of the pond. And this pond is filled with pure water. Pure water. Right. If I read again, consider a pond of cross-section 2 meters into 2 meters and containing pure water constantly being exposed to direct sunlight. Amount of solar heat radiation falling on the pond is 1000 watts per meter squared. Now the solar heat, it's kind of electromagnetic wave. Solar heat incident on the pond. The solar heat incident on the pond. Solar heat. Now we can't see the cross-section area of the pond. So therefore, if I draw when someone is looking from the top, just think you are an eagle. When you are flying on the sky and you are looking at the pond, when you look at the pond, the cross-sectional area of the pond, the top view would be like this. The top view would be like this. The top view. Correct me? Someone is looking from the top. The pond appears as a rectangle. Then the length of the pond is 2 meters. The width is also 2 meters. The given data. Right. So then when you consider top surface of the pond, 2 into 2, 4 meters squared area. 4 meters squared top surface. If not, the pond water surface area is 4 meters squared. Water surface area is 4 meters squared. That 4 meters squared water surface area is exposed to the sunlight. Exposed to sunlight. Right? Okay. Right. Okay. They mentioned amount of solar heat radiation falling on the pond is 1000 watts per meter square. Now, watts per meter square means, remember, now they have given, you can remember. Now in intensity. Intensity means what? Intensity means, you can remember, we learned equation. Intensity means power over area. If not, I told you that intensity means energy over area in time. Energy over time is the power. Therefore, normally we say that intensity means power over area. Just roughly remember, intensity means power over area. What is the units of intensity? The units of intensity is power measured in watts, area measured in meters squared. Units of intensity will be what? Watts per meter squared. Watts per meter squared. The simplest idea is intensity means when you consider 1 meter squared of area, what is the power? What is the power passing through that area? When you consider 1 meter squared of area, what is the power passing through that area? In the question they mentioned that solar heat radiation falling on the pond is 1000 watts per meter squared. Now that top surface of the pond is exposed to the sunlight. When you consider 1 meter square of area, solar radiation power, solar heat power, incident 1 meter square area is how much? 1000, right? Now they have basically given the intensity. Intensity, they have given data. Capital P means 1000 watts per meter square. What is the meaning of that? When you consider 1 meter square of area, the solar power incident is 1000. That is the idea. We know the total area exposed to the sunlight is 4 meters square. Total area exposed to sunlight is 4 meters square. 2 into 2 2 by 2 4 meters square. Still, I didn't read the question. I'm understanding what's happening here. Right. Okay. Right. Furthermore, assume that the solar heat is incident normal to the water surface. Right. Now, the solar heat, this is the water surface. If this is your water surface, solar heat, if not solar radiation, incident perpendicular to the water surface. Incident perpendicular to the water surface. That idea, right? That is also clear. That is also clear, right? Okay, right? Okay, okay. And no heat transfer occurs between water and the walls. No heat transfer occurs between water and the walls. I will explain when it is needed. And that no heat is absorbed by the water directly from sunlight. No heat is absorbed by the water directly from sunlight. Okay. All the heat is absorbed by the blackened metal sheet placed at the bottom of the pond and then transferred to water near the bottom of by conduction. This is a kind of hypothetical question. In practical, this can't be. In practical, it can't be. Now they are telling, now anyone can understand, when this water pond is open to the sunlight, what will happen? The water on the top, then little by little, the bottom of the water absorbs the solar heat, absorbs the sunlight. Then their temperature will rise. Because the water layer closer to the water layer exposing to the sunlight directly, first of all, water layer exposed to the sunlight only heats and increase its temperature. The little by little only the latter part of the water layers also get heated. But in the question they are telling, think like this, think like this. Now we are sun, solar radiation. If not heat is falling on the water pond only, but they are telling, consider initially all the heat, all the solar radiation incident on the pond, first of all absorbed by a black color plate at the bottom. It's wrong. So there's a black color plate placed at the bottom. Is the plate. So they are telling us to consider all the heat, all the solar radiation initially absorbed by the black color plate placed at the bottom. From that black color plate only, heat is propagating to the water by conduction. Actually, it's wrong. This side is very wrong. The right way is, first of all, by absorbing the heat, the top surface of the water gets heated. Then the next surface of the water, next layer of the water, next layer of the water. Finally, only this black color plate gets heated. But they are telling us to assume all the heat initially absorbed by the black color plate, then black color plate only releasing that heat to the water. Actually, water gets heated because of the heat released by the black color plate. So you want to think like that, right? You want to think like that. That is the idea. That is the idea, right? Okay. Now we can do the question. Now, Roman number 1, what they are asking? Roman number 1, they are asking, if the amount of heat absorbed by the metal sheet over a 7-minute period, if the amount of heat absorbed by the metal sheet over a 7-minute period entirely contributed to raise the temperature of the thin layer of water of mass 40 kilogram just above the metal sheet, how much will be the temperature in water? Temperature rise in water. Take specific heat capacity of water is 4,200 kilograms per kilogram per Kelvin. Look here. Now, as I already explained, heat is released by this metal plate. Is the metal plate. Learn from these questions. This is the metal plate. And they are talking about a water layer adjacent to them. If you're nearby the metal plate, that's a water layer. The water layer is the water layer nearby the metal plate. So then, as I already explained that, heat is released from the metal plate to this water layer. Actually, heat is released from the metal plate to this water layer. Right. And they have given the mass of this water layer is how much? 40 kilograms. Mass of this water layer is 40 kilogram. Simply means 40 kilograms. And they have given the specific heat capacity of water. Right. They have given the specific heat capacity of water. They are asking the amount of heat absorbed by the metal sheet over a 7-minute period entirely contributed to raise the temperature of a thin layer of water of mass 40 kilogram just above the metal sheet. How much will the temperature rise? Okay. Then first of all, you want to understand within that 7-minute time period. Within that 7-minute time period, you should find the amount of heat absorbed by the metal plate. Within 7-minute time period, first of all, you should find the amount of heat absorbed by the metal plate. I told you all the heat directly incident on the metal plate. We know that when you consider 1 meter squared of surface, power of heat is 1000 watts. If you want to find the total power of the heat incident on the metal plate, now you want to assume that. Now you want to assume here metal plate also, the surface area of the metal plate also equal to the free surface area of the bond. Now you want to assume that the surface area of the metal plate also equal to the free surface area of the bond. Right? If this is your top surface of the pond, metal plate also has the same surface area. Then we can easily find within 7-minute time period amount of heat absorbed by the metal plate. So you write down amount of heat absorbed by the metal plate. I just mark it as QM. We know the equation. We know the equation. Power means we know. Power means we know that. Right. Intensity means I told you. Intensity means we can write down energy over area into time. This equation. My target is to find the amount of heat energy. Amount of heat energy absorbed by the metal plate within 7-minute time period. We have given the intensities. How much? Intensity is 1000. Intensity is 1000. Then within 7-minute period, the amount of heat absorbed by the metal plate, let's say QM. Amount of heat absorbed by the metal plate is QM. Then the surface area of the metal plate is how much? 2 by 2 means 4 meters squared. The time taken is 7 minutes. But normally we convert time into seconds. How do you convert minutes into seconds? Multiply by 60. Multiply by 60. Right, then when you subject QM, QM means amount of heat absorbed by the metal plate within 7-minute time period. If you subject QM, you get the answer. What is QM then? Subject QM. Subject QM. Subject QM. Subject QM. Subject QM. So if you subject QM, someone tell me this value. Simplify it and take a calculator and simplify and tell me the value. Subject QM. QM is how much? 4 into 7 into 60. 4 into 7 into 60 into 1000. 1000. Then unit is in joules. What is the answer? The answer is how much? 7 into 6 means how much? 42. 42 into 4 means how much? 168. 168. 10 to the power 1 and the power 4. Someone check this value. 1.68 into 10 to the power 6 joules. Genuinely hands up. Now still I didn't do the question yet. Now this is what amount of heat absorbed by I told you that solar radiation incident first of all to the plate. Then that heat only transfers to the water. Now what I have done is within 7-minute time period, I found the amount of heat incident on the metal plate, amount of heat absorbed by the metal plate. They have given that intensity. They have given that intensity. It's not power. They have given the intensity. Power over area means intensity. From this equation, I found the energy, amount of heat energy absorbed by the metal plate within 7 minutes. That idea is clear answer. This is clear answer. This story. This idea is clear answer. Someone please cross check this simplification. This idea is clear answer. This idea is clear. This idea is clear. I shared the PDF in the group. Right? But I'll share the PDF in the group again. Right. Share the PDF in the group again. Okay. But they are asking now that the heat absorbed by the metal plate is this much. Within 7-minute time period, heat absorbed by the metal plate is this much. Now this heat is going to supply to the water layer of mass 40 kilogram. Then they are asking in that case what will be the increase in temperature of the water layer? What will be the increase in temperature of the water layer? Then what you can do? Now who is going to absorb the heat? Water absorbs the heat. If you want to find the amount of heat absorbed by an object or amount of heat released by an object, we can use an equation. Q equals mx delta theta. So Q equals mx delta theta. You want to apply this equation for water layer. Water layer, water. Water layer, if not water. Water layer, if not water. Then within 7-minute time period, metal plate absorb this much of heat energy. That heat energy entirely absorbed to the water. Then Q is how much? 1.68 into 10 to the power 6. Mass of the water layer is 40 kilograms. 40 kilograms. Specific heat capacity. Specific heat capacity of water is, they have given that 4200. They are asking us to find the rise in temperature. The rise in temperature delta theta. The rise in temperature delta theta. Delta theta. Subject delta theta. Do you get the answer? Just simplify, tell me the answer. When is subject delta theta? Now this is, I can write as what? 1.68 into the power 6 means. 1.68 into 10 to the power 6 means I can write down 4 into 7 into 60 into 1000 over 40 into 4200. 4200. Right. So then we know that 7 into 6 means how much? 7 into 6 means 42. 7 into 60 means how much? 420. Right. So this 420 and this 420 cancel out. 1 this 0 and this 0 cancel out. This 0 cancel out. These 4 cancel out. What's remaining then? The remaining is 10. The only remaining is 10. Answer is 10 Celsius. The temperature rises 10 degrees Celsius. The temperature rises 10 degrees Celsius. Hands up. Idea is clear, hands up. This question, first part is clear, hands up. Genuinely. Genuinely, if you understood, hands up. Raise your hands. Right, okay. Then that part is done. The next we'll go to next one. Roman number 1 done. Roman number 2. Roman number 2. Let density of water at 0 degrees Celsius and 300 degrees Celsius be rho naught and rho theta respectively. Obtain an expression for rho theta in terms of rho naught, theta, and the volume expansivity of water gamma. Volume expansivity of water gamma. Right, okay. Look here. Roman number 2. Next story. Next story. There is a water. There's a water sample. let the densities of water 0 degrees Celsius. Okay, there is a water sample, right? Initially, this water sample is at 0 degrees Celsius. Then this water absorbs heat energy. Then we know what will happen. When this water absorbs heat energy, we know that. When this water absorbs heat energy, we know that temperature of the water will increase. Temperature of the water will increase. Temperature of water will increase. Temperature of the water will increase. Water absorbs heat energy. Then we know that temperature of the water will increase. Let's say now temperature of the water is, let's say theta. Now temperature of the water is how much? Theta degrees Celsius. Theta degrees Celsius or theta. Then we know that when this water sample mass doesn't change, right? Just because you supplied heat, mass of the water sample doesn't change. Mass remains constant. Mass remains constant. So therefore, remember these stories. I derived this equation, the relationship between rho theta and rho naught, this equation in the theory classes. But that's fine. Let's say mass doesn't change. Mass remains constant. Remember, mass of the water sample remains constant. But we know that when water absorbs heat, it undergoes expansion. It undergoes expansion, then volume increases, then volume increases. Then we can remember the equation. When volume increases, we can remember density means mass or volume. Even though mass remains constant, we know that when volume increases, we learn that density of the water decreases. When the volume increases, density of the water decreases. This idea we can remember. We can remember. We can remember. Now they mentioned, that's why they mentioned that when the temperature is 0 degrees Celsius, density of the water is rho naught. Density of the water is rho naught. When the temperature of the water sample is theta degrees Celsius, density of the water is rho theta. Then if I ask you what is the change in temperature, initial temperature is 0, now temperature is theta. Change in temperature means theta minus 0, that is theta. And they have given volume expansivity as gamma. So they are asking relationship between rho theta, not gamma theta. But we remember that in liquid expansion, we learned that the relationship between final volume and initial volume. Let's say final volume is V2, initial volume is V1. Then you can remember that V2 means V1 inside the bracket 1 plus gamma delta theta. I told you to remember. If you want to obtain a relationship between final volume of the liquid and initial volume of the liquid, if the liquid undergoes expansion due to the supplied heat, then we can write down volume expansion equation, popular equation, right? So V2 equals V1 1 plus gamma delta theta is the equation. But they are asking us to derive an equation for density relationship. But we all know that the V2 means final volume. V2 means final volume. Let's say this is V2. This is V1. V2 is final volume. Now, we know volume means for this equation, we can tell that volume means subject volume. Rho means mass or volume. If we subject volume, we all know that volume means mass or density. We all know that volume means mass or density. Right? Simple M over density, final density means it's rho theta. It's rho theta must be equal to initial volume is V1. Then tell me initial volume V1 in terms of mass and density. Mass doesn't change, simple in mass only. Initial density is how much? That is rho naught. Rho naught 1 plus gamma delta theta. Change in temperature means final temperature is theta. Initial temperature is 0, theta minus 0. Then we can write down simple m cancel out. They're asking us to write an expression for rho theta. Substitute rho theta. If you substitute rho theta, we can write down. Rho theta means what? Rho theta means rho naught over rho naught over 1 plus gamma theta. Done. Done. That story is done. That's Roman number 2 is discussed. Roman number 2 discussed. Roman number 3. Explain why convection currents will occur. Explain why convection currents will occur when water is heated as mentioned in A Roman number 1. As mentioned in A Roman number 1. Right? Okay. Convection currents. Can you remember when I was explaining heat under convection? Under convection, I told you that convection currents. I will tell that Roman number 3. Roughly I revise it. Roughly I revise it. If you can do the classes until 1 a.m., nice. Since last few months. Okay. I told you right. So when there is a heated object placed in a surrounding, then this object has a larger temperature. Surround temperature is smaller. Then we know that heat dissipates from object to the surrounding. Heat dissipates from object to the surrounding. Then I explained that. Can you remember? Then I explained that heat dissipates from object to the surrounding. Then what will happen? This heat gonna absorb by the nearby particles, nearby air particles. When those air particles absorb those heat energy, what will happen for the volume of those nearby air particles? Volume of those nearby air particles will increase. Then what will happen for the density of that nearby air particles? What will happen for the density of nearby air particles? When the volume increases, density of nearby air particles, density of nearby air particles decreases. When you compare with the density of normal air particles, if not air particles far from the object, when you compare with the density of air particles far from the object, now the nearby air particles density is lesser. As a result, we know that less density substances always try to go upwards. So therefore, these nearby air particles absorb the heat. Now, they are not just going upwards. They are carrying that absorbed heat, and so they are going in upward direction. So then I told you that in this region going to fill with the far particles. Same thing is repeating story. I told you. I told you. Then this flow of heated air particles in the upward direction is I told as convection current. Now they are asking, now in this scenario, relate that. In this scenario, now they are telling Roman number 3. Roman number 3, Roman number 3, they are telling that explain why convection current will occur when water is heated as mentioned in A Roman number 1 above. How water is heated in A Roman number 1 above? There is a metal plate at the bottom. Metal plate only supplies the heat. Then we know that metal plate first of all supplies the heat to the nearby water layer. First of all, metal plate supplies the heat to the nearby water layer. Then what will happen? Then we know that as we learned so far, when the metal plate supplies heat to the nearby water particles absorb the heat, volume of the water particle increases, density of the water particle decreases. Now comparing with the water particles here, comparing with the water particles here, now these water particles have low density. If they are low density, these water particles absorbed heat. The water particles have low density. They try to go upwards. They try to go upwards, right? They try to go upwards. Same scenario. Then what will happen? Then this region going to be empty. That empty region going to occupy by the nearby water layer. The nearby water layer also absorb the heat. Nearby water layer also volume increases, density decreases, nearby water layer particle also goes upward. Then the top layer will come to the bottom. So likewise, what's happening? This heat is propagating from bottom to the top. This heat is propagating from bottom to the top. This is the idea. Idea ni? That is the idea. Problem number 3 also done. Done, you write on can't give, cannot write. Done. Simple B. Simple B story. Simple B story. Done. Okay. Simple B story. Simple B. Up now everything is crystal clear and up now everything we discussed so far crystal clear and everything is very clear and everything is very clear and everything is very clear. Everything is very clear and everything is very clear. Right? Okay. Right? Okay. Simple B part. Simple B part. Start thinking. Just try to do the simple B part. Give me 1 second. Try simple B part. Try simple B part. Try simple B part. Just try simple B part. right? Just try simple B part. Simple B part, right? Simple B part, right? Okay, right, right. Simple B. Simple B, what they're asking. Mm, simple B. Then a solar pond is a pond used to collect and store solar energy. Solar pond means a pond used to collect and store energy, used to collect and store solar energy as heat. Okay. Solar heat reaching the bottom of such a pond is tapped by a suppressing convection currents. Is tapped by suppressing convection currents. Solar pond is a pond used to collect and store solar energy as heat. That means somehow that pond, now we know that there's a pond. That pond is open to the surrounding. That pond is exposed to the sun radiation. Then when the heat incident on the water layers, what's happening? Somehow all the heat going to absorb by the water layers, right? Somehow that pond is going to store that solar energy. Somehow the pond is going to store solar energy, right? Uh, right. Solar heat reaching the bottom of such pond is trapped by suppressing convection currents. A very simple model of a solar pond with a 2 by 2 area is shown in the figure, right? Figure 2. Now, when look at the figure 2, when look at the figure 2, there's the same pond, but they have considered some layers, right? So they have demarked some kind of layer, set of layers. There are 3 layers, something. Okay, right. It has three distinct layers. The top layer has relatively pure water. Top layer has relatively pure water. The bottom layer has a very high soil concentration resulting in a high density. The density is uniform throughout the layer. In the middle layer, the soil concentration and density decreases gradually with height. Gradually with height. Gradually with height. For the following parts, assume that the initial temperature of water throughout the pond is 30 degrees Celsius. For the following parts, assume that the initial temperature of water throughout the pond is 30 degrees Celsius. First of all, I do the diagram and I try to understand what they are telling. I try to understand what they are telling. Now there is a water pond. They are talking about 3 different layers in the water pond. There are 3 different layers in the water pond. 3 different layers. Layer 1, layer 2, layer 3. Now they mentioned topmost layer has the lowest density. Topmost layer is full of pure water. Topmost layer is full of pure water. Right? Lowest density. Topmost layer is full of pure water. Topmost layer. And the bottom layer has because of the soil concentration at the bottom layer. Density of the bottom layer is large. That's obviously. Normally, when you go to the bottom layers, the layer at the bottom has larger density normally. Right? Now, bottom layer has larger density, top layer has lesser density. When you consider middle layer, they are telling from bottom to the top. If you consider the middle layer, from the bottom to the top, density is decreasing. Density is decreasing in the middle layer from the bottom to the top. That's okay. Understandable. Yeah, we have kind of idea. Okay, densities are different. Simply you are telling the bottom layer has different density. You are telling top layer has different density. Even though they are water, because of soil concentration, they like some kind of different liquids. They are some kind of different liquids. For example, coconut oil and water. Some kind of idea. Take some kind of idea like that. Okay. So far, idea is clear. Then the surface area. The area of the pond exposed to the surrounding is same as 2 by 2, 4 meter square surface area. 4 meter square surface area. Right, okay. Idea, okay. Idea okay, right? Okay. Now they mentioned that initially all the layers have same temperature, 30 degrees Celsius. Initially, all the layers have same temperature. Let's say initial temperature is theta 1 something. Theta 1 something, that is 30 degrees Celsius initially. Top layer or middle layer or bottom layer, they all at the same temperature. They all at the same temperature. Right, okay. Okay. Right. Okay. Right. Problem number 1. In a practical solar pond, temperature of the bottom layer can reach about 90 degrees Celsius. Now, initially, I think before absorbing the heat, before the pond absorb the heat, initial temperature of bottom, top, and middle layers are 30 degrees Celsius. When pond absorbs heat, they are telling in practical solar pond, the temperature of the bottom layer can reach about 9 degrees Celsius. If the mass of the water in this layer, mass of the water at the bottom layer, the mass of the water at the only bottom layer, 6,000 kilogram, and if it receives heat radiation at a constant rate of 1000 watt per meter squared, same story. How long will water take to reach 9 degrees Celsius? That assume and okay, right? Assume that heat is entirely used to increase the temperature of the water, and that salt water has the same specific heat capacity as pure water. Right, okay. Now I understand. Somehow, initially, just think about the bottom water layer. Just think about bottom water layer. They have given mass of the bottom water layer is how much? 6,000 kilograms. Mass of the bottommost water layer as 6,000 kilograms. And we know that initially, bottom water layer is at a temperature 30 degrees Celsius. Now we know this bottom water layer absorbs heat. Bottom water layer absorbs heat. According to this scenario, I think there may be a there may be a black color plate at the bottom. Then that heat is transferred to the bottommost layer, right? Okay. Somehow, bottom water layer absorbs heat, and its temperature increases from 30 degrees Celsius to 9 degrees Celsius, right? Bottom layers, if I consider bottom layer, its temperature increases from 30 degrees Celsius to 90 degrees Celsius. They are telling us to consider specific heat capacity of bottom water layer is same as 4200. Then we can easily find what? We can easily find the amount of heat. Now, when the temperature of the bottom layer increases from 30 to 90, we can find the amount of heat absorbed by the bottommost layer. Correct me? Now, we know the mass, we know the specific heat capacity of bottom water layer. We know the temperature difference. Initially, it was at 30 degrees Celsius. Now, bottom layer is at 9 degrees Celsius. Then we can find the amount of heat absorbed by the bottom water layer to obtain 90 degrees Celsius. We can apply what equation? Q equals m delta theta. They are asking me something else. That's okay. Q equals m delta theta. Then mass of the bottom water layer is 6,000 kilograms. Specific heat capacity of the water is 4,200. Temperature difference. Initially, bottommost layer was at 30 degrees Celsius. Now the temperature of the bottom water layer is 90. Temperature difference means final temperature is 90, initial temperature 60, 90 minus 60. Temperature difference. So when you simplify this, you will get an answer. This is the amount of heat absorbed by the bottom water layer. In the question, they are asking something else. In the question, they are asking how long bottom layer take. The question they are asking, how long will water take to reach 90 degrees Celsius? They ask the time period. From 30 degrees Celsius to increase the temperature from 30 to 90, how long will the bottom layer take? Then time, want to involve time. I know the heat absorbed by the water layer. If I want to involve time, all right. Then I know the heat energy. And they have given intensity. Right? So they have given intensity, then I can link the equation. So we know that heat intensity means, we can remember intensity means energy over area into time. I know intensity is 1000. E means heat energy. E means heat energy. Heat energy absorbed by the what? Water layer. Area means surface area. So when you substitute the time, you get the answer. When you substitute the time, you get the answer. First of all, I subject time. I subject time and I find the time first. Then I will explain the story again. Sometimes some of you not very familiar with this intensity scenario. Intensity given is how much? 1000, and heat is absorbed. Heat is 6000, 4200 into 60 over surface area. Surface area is, it's 4. I want to find simplicity. I want to find simplicity. Simplicity. So if you subject simplicity, you get the answer. Subject simplicity. If you subject simplicity, you get the answer. Subject simplicity. Subject. Subject. Simplicity. Simplicity is how much? Simplicity is 4 into 1000. We can cut these 3 zeros, cancel out. Then I can say 4 over. So the simplicity means what? Simplicity equals, if I subject simplicity, right? Now 6 into 4200 into 6 into 4200 into 60 over 4. 60 over 4. Right? What is the answer? Someone check the answer. Someone check the answer. How much? Now what can I do now here? If I divide by 4, then it's here 15. 15. 15 into 6 means 90. Am I correct? 15 into 6 means 90. 4200. Then we are getting an answer. 3 zeros. 9 into 2 means 18. 36, 37 something. Someone check this answer is correct. This answer is correct. This answer is correct. Hands up. How many of you say this answer is correct? Hands up. This answer is correct. Hands up. How many of you say this answer is correct? Now stay focused. Huh? This answer is correct. Hands up. Quickly. Hands up quickly. Hands up quickly. Hands up quickly. Someone check and tell me. Others. Any mistake? No, right? Correct me? Correct me? Right. Okay. Now, okay, look here. Now, this story, okay, I will explain a little bit different way. Now we understood that this bottom water layer has to absorb heat, Then how this bottom water layer absorbs heat? I think this bottom water layer absorbs heat from the metal plate at the bottom, because we know metal plate only supplies heat. Okay, we considered how initially solar radiation directly enters to the metal plate kept at the bottom. It's wrong, but we have to consider like that, right? Initially the solar radiation directly incident at the bottom, metal plate. Okay, then what is the area of the metal plate? The area of the metal plate is, we all know that 2 by 2 means 4 meter squared area. The area of the metal plate is 4 meter squared area. Okay, then if I draw kind of 3D diagram, this is your this has your black color metal plate. Then the surface area of the black color metal plate is 4 meters squared. Solar radiation, just think, directly incident perpendicular to the metal plate. Directly incident perpendicular to the metal plate. Right. We all know that they have given the intensity of solar radiation. What does it mean by intensity of solar radiation? The idea is 1 meter squared area. When you consider metal plate area, when you consider metal plate area, if you take 1 meter squared of area in the metal plate, remember, if you take 1 meter squared area in the metal plate, we know metal plate total surface area is 4 meters squared. Throughout this 4 meter squared surface area, solar radiation incident. When you consider 1 meter squared area of the metal plate, when you consider 1 meter squared area of the metal plate, solar power incident on is the solar power incident is 1000 watts. That is the idea of intensity. 1 meter squared of area, how much solar power incident? 1000 watts. That is what we call as 1000 watt per meter squared. 1000 now they have given intensity as how much? 1000 watt per meter squared. That means when you consider 1 meter squared of surface area, how much solar power incident on that area? That is the idea. Then we can tell that for 1 meter squared of area, incident solar power is 1000 watt. Since there are 4 meters squared of area, total solar power incident on 4 meters squared area will be how much? That's going to be 4000 watts. That's going to be 4000 watts. Now this is directly substituting. If not, I am doing a different way. Then for the entire surface area of the metal plate, solar power incident on the metal plate is 4000 watts. Right? Now, who is going to give the heat to the bottom of the water layer? The metal plate. We found what is the amount of heat absorbed by the bottom of the water layer. Amount of heat absorbed by the bottom water layer is how much? This much. Who is going to give this much of heat? This much of heat is going to give by metal plate. Now what you can do for the metal plate? No, I am doing a different way. For the metal plate, what you can do? For the metal plate, what you can do? You can apply what? You can apply power equals energy over time. Right? Solar power is on the metal plate is 4000 watts. Then when 4000 solar power incident on the metal plate for simple t time period, the amount of heat absorbed by the metal plate is how much? That is this much. 6000, 4200 into 60. Then when you substitute simple t, same story. The same story only. Hands up, this idea is clear answer. This idea is clear answer. All this idea very clear answer. This is very clear answer. Very, very clear. Please learn at least these few days. Get the maximum benefits. Okay, problem number 2. Now last few sections. Problem number 2, right? Take rho naught as 1554 for the salt water and calculate the density of salt water at 9 degrees Celsius. Okay, that is easy. There is substitution. So we in this equation, I erase this part. Maybe it might be important. In that case, you need to support me. I'm erasing this part. If I erase this part, problem number 2. Problem number 2. Problem number 2. Then here. So we derive the equation. Rho theta means what? Now remember this equation, learn by heart. Rho theta means rho naught 1 plus gamma theta. 1 plus gamma theta means delta theta. 1 plus gamma theta. Okay. Right. Okay. They are telling taking rho naught as 1554 kilograms per cube. That means density of the water at 0 degrees Celsius is 1554 for salt water. And they are asking us to find the density of salt water at 9 degrees Celsius. Then you are going to find rho 90. Theta means now temperature. Now temperature is 9 degrees Celsius. Then you are going to find rho 90. Rho 90 equals rho 90 degrees Celsius equals density of the salt water at 0 degrees Celsius. They have given 1554. over 1 plus volume expansivity is how much? 4 into 10 to the power minus 4. Volume expansivity is 4 into 10 to the power minus 4 into change in temperature. Now, many people do a mistake here. Many people do a mistake here. If I ask you to substitute theta, some of you might substitute. Here's a, you told that 1 plus gamma delta theta. So you told that 1 plus gamma delta theta. Delta theta, delta theta means you told us final temperature minus initial temperature. So in this scenario, final temperature is 90, initial temperature is 30, sir. So therefore, I am putting 90 minus 30 is 60. I am putting delta theta as 90 minus 60 is wrong. Why? This equation is derived considering density of water at 0 degrees Celsius and density of water at 0 degrees Celsius and density of water at 3 degrees Celsius. Now we are going to take the difference between theta Celsius temperature and 0 degrees Celsius. The difference is always theta minus 0. Now your theta is 90, initial temperature means 0. Therefore 90 minus 0 means 90. Okay. Now simplification is there. Now 1554 over. Now here 90 into 4 means 360. 360 here 360. 9 into 4 means 360. 0 360 to the power minus 4 means how much? 1.036 something. Just can someone take your calculator and tell me what the value of this one? Quickly take your calculator and tell me the value. Someone quickly 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 tell me the value. Quickly. The value. Anyone? I don't have a calculator now. Someone quickly tell me the value. Someone quickly tell me the value. 1500. Exactly. Exactly. We are getting answer as 1500. Please read this question once again. kg m minus 3. Okay. That is done. Next one. Last three Roman number parts. Last three. See, not difficult. Everything I taught. The practice is important. If you have enough practice, exam questions are not difficult. Right? These days we will do essay questions also. I have to do sessions. Roman number 3. Roman number 3, okay. Now they are telling next story. In the top layer remains at 30 degrees Celsius. If the top layer remains at 30 degrees Celsius, can there be convection currents? Can there be convection currents from the bottom layer to top layer under above condition? Under above condition. Justify your answer. Take density of pure water at 30 degrees Celsius is 1000. Very simple. Initially they told that there is a pond. There are 3 different layers in the pond. The topmost layer is pure water having low density. The bottom layer is having high density due to the soil concentration. Right? So bottom layer is concentrated with salt. This is the intermediate medium. Now we noticed in the beginning all the 3 layers were at same temperature theta 30 degrees Celsius. All the layers were at same temperature 30 degrees Celsius. Now they are telling, then what happened? Then we supplied heat only to the bottom layer. Right? They are telling when you supply heat to the bottom layer, if the temperature on the top layer remains same as 30, right? Now you are keep on supplying you keep on supplying heat to the bottom layer. Bottom layer temperature rises from 30 to 90, but still top layer temperature remains at 30. But in practical, it can't be. In practical, that heat is propagating upwards. In practical, what happens? Temperature of the top layer also increases. But they are telling even temperature at the bottom layer increases from 30 to 90. Top layer is still at the temperature 30. Then when the top layer is at 30 degrees Celsius, density of top layer, density of water at top layer is 1000. Now we know bottom layer has obtained 90 degrees Celsius. Just now we found that density of the water at the bottom layer is 1500. I told you this convection current happens. This convection current happens by absorbing the liquid or air particles. They undergo expansion, their density decreases. As a result of decreasing density of the particles, only those particles go up as kind of convection current. But in here we noticed, is it possible for the bottom water particles to go upwards as a convection current? Do you think that is it possible for the bottom water particle to go upwards as a convection current? Can't. Because why? Still, even the temperature is 90, still density of the bottom water particle is 1500. Top water particle density is 1000. Still, dense, even though bottom water particles are heated to 90 degrees Celsius, still bottom water particles have high density. If the bottom water particles have high density, how can bottom water particle go upwards? So therefore, no bottom water particle go upwards. If nothing going upward means no convection current. Roman number 4. Roman number 4. Number 1. The Roman number 3 I explained. Number 4, number 1. Roman number 4. Number 1. Story. When the temperature of the bottom layer increases from 30 to 90, calculate the amount of heat stored in that layer. I already have calculated. Right? Roman number 4, number 1, they are telling when the temperature of the bottom layer increases from 30 to 90, calculate the amount of heat absorbed by the, stored by the layer. Then Q equals m delta theta. This is the answer. So what will be the answer? This Q is how much? This Q value. What is when you simplify it? I think we got how much? We simplify this value. Q equals 6000 into 4260. 6000 into 4200 into 60 means how much? 60 means how much? Tell me the value. Now here 1, 2, 3, 4, 5, 6. 10 to the power 6 into 6 into 6 means 36. 36 into 42. Then here it's 12. Here 25. Here it's 6. Here it's 12. 2, 11, 5, 1. Just check, huh? 1512 joule something. Normally we keep in science notation 1.512 10 to the power 9. Someone cross check. 1.512 10 to the power 9 joules. Someone cross check this value. Someone cross check Q value. Next story. Number 2. Under number 4, number 1 discussed. Number 2. Number 2. Suggest a method to use this energy for practical purpose. Now what you can do normally, you can come up with your own method. Now you are storing this heat. Now there is a water pond. In that water pond, at the bottom layer, you stored heat. The bottom layer is heated. You stored heat. Then what you can do now, how are you going to use that heat energy? Now you can go different steps. One can tell that by allowing by absorbing that heat to the water passing through a pipe, you can heat something else, you can generate power or whatever. You can tell some examples. Now there are many. Even you write your own ideas also. Sometimes you get the answer and they give marks also. Last section. Last story. Easy. Last story is easy. This question again revised all the convection stories and conduction. In a practical solar pond, heat loss to the walls must be minimized. It's true. Now, this is your pond. Now, somehow, let's say that heat is first of all entering the metal plate, then metal plate is supplying that heat to the water layers. But we know after when the water layer is absorbing the heat, some amount of heat is passing through the walls. Some heat is what? Not only absorbing by the water, some heat is passing through the walls to the surrounding. Right. They are telling in a practical solar pond, the heat loss through the wall must be minimized. If a rigiform, I think, if a styrofoam layer of thickness 10 centimeter is used as an insulation between water and the walls of the pond, rigiform something, rigiform layer, styrofoam layer of thickness 10 centimeter is used as a insulation between water and the wall. Water and the wall. Now currently there is water and the wall. There is water. See, water and the wall. They are touching each other. Rather than touching them each other, you are going to put a kind of insulation layer between. Okay, why? To reduce the amount of heat loss to the wall. Okay, right? Thickness 10 centimeter, insulation between water and the wall of the pond. And if the temperature of the wall stay at 4 degrees Celsius, temperature of the wall stay at 4 degrees Celsius, a wall temperature 40, water is 90. Bottom water is 90, water is 90, wall is 40. What will be the rate of heat loss per meter square through the styrofoam? Not difficult, I will tell you. Not difficult, I will tell you. Okay, the last part. Then story finished. Then we'll do next essay question. The last part, not difficult, very easy. Now this idea, conduction story. The conduction story. The last part is Roman number 5. See the idea. See the idea. Idea. There is water. There is water. Is water. Water at the bottom layer, thing like that. This is water at the bottom layer, whatever. In between water and the wall. So what is this? This is the wall. Here after wall. Now earlier, water was in contact with the wall. Then we noticed that a considerable amount of heat dissipated to the wall. Now this is your water. This is your wall. Who is in between the water and the wall? Insulation layer. This is your insulation layer. Even though you added kind of insulation layer in between water and the wall, also there is a heat loss. Why? Temperature of the water is 90 degrees Celsius. It's a theta 1. Temperature of the water is 90 degrees Celsius. Temperature of the wall is 40 degrees Celsius. Whenever there is a temperature difference, definitely heat passes from high temperature to low temperature. Definitely there will be heat loss. No doubt that no matter you put how many insulation layers, obviously there is a heat dissipation. But why we are putting insulation layer? We are going to reduce the amount of heat dissipation. Without putting insulation layer, let's say heat dissipation per second is 500 joules. If we put the insulation layer per second, heat dissipation will be 10 or 20 joules. Right? We can reduce the amount of heat dissipation. That is the idea. Remember, whenever there's a change in temperature, definitely heat passes. If you want to not, in order to avoid heat passes through the layer, then temperature of the water and temperature of the wall must be same. Then only heat won't transfer. Whenever there's a temperature difference, 90-40, definitely heat passes from high temperature to low temperature. It passes from high temperature to low temperature. Okay. Okay, right. So they are asking in the question, last part done. They are asking the question, if the temperature of the world stays at 40 Celsius while the water is at 90, what will be the rate of heat loss per meter squared of styrofoam? That means when you consider 1 meter square. Now, this is the side view. If I only do the styrofoam, look here. I do the styrofoam layer. This is a styrofoam. The styrofoam layer. This is the styrofoam layer. It's red color is styrofoam layer. Okay. Red color is styrofoam layer. Huh? Now here is water. Now here is water. This is water. Nee? This is wall. Understand idea? Thickness we know. Nee? Thickness we know. And now, when you consider, now we know that then water temperature is 90, wall temperature is 40. Then we know he dissipates through the wall. He dissipates through the wall. Sorry, he dissipates through the styrofoam layer to the wall. Nee? He dissipates from the water to the wall through the styrofoam layer. When you consider 1 meter, now just think this area of the styrofoam layer is this area. We know heat is perpendicular to the styrofoam area. Look here. Is the heat propagating perpendicular to the area? If you take this area is 1 meter squared area. If this area is 1 meter squared area, if this area is 1 meter squared area, they're asking what is the what when the area is 1 meter squared, what is the rate of heat conduction? They're asking Q dot. Then we know the conduction equation. We know the conduction equation. Q dot means what? Ka delta theta over delta L. We know area is 1 meter squared. K they have given delta theta means 90 minus 40. Thickness given 10. Simple. Final answer. Final answer is K is 0.01. Then area is 1 meter squared. Delta theta means how much? 90 minus 40. Delta L is how much? Delta L is the thickness. This heat is passing through a thickness of 10 centimeter. 10 into 10 to the power minus 2. Right? So if you simplify, actually you are getting, if you simplify it, you are getting what? You are getting actually 5 watts per meter squared something. Hands up, the story is crystal clear. Hands up. 2012 A level essay question is very clear. Hands up. 2012 A level essay question is very clear. Hands up. Right? Learn from this, prepare some short notes and everything. Now same question is they are changing and asking. Right? So we'll take a small 5-minute break and we'll ready for the next question. Time is 11:23. We'll take a small break and get ready for the next question. Huh? Again, we'll start 11:28 or 9 something. Just write down these things. Right, okay. So then 2012 done. Now we'll do the next essay question and right. Next essay question is 2000. Maybe it may be complex, but not that much complex also. Right. 2014, 11, 2014, 14. Right. Now read the question. Figure 1A. Figure 1A. Figure 1A shows a parabolic disk type solar energy collector. Figure 1A shows a parabolic disk type solar energy collector. Sometimes when we hear these devices names also, we feel like we have no idea. Sometimes we drop this question also. But don't you think called physics is always like that only? They give a new device, they tell different, very unfamiliar names. But the application, what we want to do is very basic, right? Figure 1 shows a parabolic disk type solar energy collector. So by the name, I can understand solar energy collector means that device is collecting solar energy. That means the device is collecting heat energy. That type of idea only I am having when I read the word solar energy collector. Having a circular aperture, which extracts and converts solar energy to heat. Which extracts and converts solar energy to heat. Solar energy flux is concentrated to a cavity receiver placed at the focus of the parabolic disc as shown in the figure A. Where is figure A? There is a, they are telling different names. Cavity what? They are telling cavity receiver. Cavity receiver. They are telling solar energy flux is concentrated to a cavity receiver placed at the focus of the parabolic disc as shown in the figure. Now you know that parabol disc means that is something like that POTV antenna, right? POTV, that circular shape, a kind of curvy. It's like our glass bowl something. If not, we can take our what that glass plate that we eat rice, some kind of curvy shape. Okay, 2014 level idea, not difficult. See the idea. If I draw for your understanding, now stay focused. Huh? This is some kind. You might have seen some POTV antennas also in this shape, right? So actually, eh, I hope you understand what I am explaining, right? So then, when you consider the aperture, if not just take this perimeter, this perimeter is exactly in a circular shape. This perimeter is exactly in a circular shape, right? The perimeter is exactly in a circular shape, right? That story, okay. Then what? Circular shape, circular shape, circular shape. Look at the figure 2. In figure 2, they are telling, in figure 2, they are telling, right? See, so what happened? This is our, this is the solar energy collector. This is the solar energy collector. This is the solar energy collector. Actually, what's happening? Solar rays, they are also kind of electromagnetic waves. A solar rays incident perpendicular to the collector. So what happens is these solar rays incident on the collector reflects and converges, if not concentrates, to that cavity. So they reflects and reaching that cavity. So the cavity is located exactly this focus. Now just think that there are solar electromagnetic waves incident on this plate, and they reflects all the solar radiation are collected at this point. At this point, we are placing the collector. So when you place the collector here, all the solar rays you can collect into that collector. You understand? So here is the collector. So you can collect all the solar heat, solar radiation at this. If you place the cavity at this point, you can collect all the solar heat to that cavity collector. Right? Okay. Very simple story. Okay, right? Now. Okay, right. So now very clear now, we collect the solar radiation. We collect the heat to a cavity, right? Now this cavity is full of heat. The cavity is full of solar radiation, right? Uh, an oil passing continuously through a spiral metal tube fixed to the inner wall of the cavity extracts the heat absorbed by the cavity. Parabolic disc is moved so that the solar flux always fall normal to the disc as shown in the figure. Aperture diameter, simple d, of the disc is 20 meter. Now see now what they are telling, right? Okay. After you collected that solar radiation, solar heat to that cavity collector, what we are going to do is inside the cavity collector we are sending kind of water. We are sending kind of oil. We are sending kind of they have given what? We are sending kind of oil inside the tube. Okay. So I say this is the cavity collector. For an example, this is the cavity collector. Just think like this. Then what I am doing is, if this is the cavity collector, for an example, in this inside the collector, all the solar radiation is concentrated. Now, what I am doing, there is a kind of spiral tube. Through the spiral tube, just assume oil is passing. The spiral tube is inside the cavity collector. Kind of oil is passing through the spiral tube and coming out. But we know that when that oil passing through the spiral tube, it absorbs the heat from the cavity collector. Because we know this collector is fully loaded with the heat energy. When the oil is passing through the spiral tube and when the oil is coming back to the out, it absorbs all the heat. Do you understand? How we are going to extract the heat concentrated in the cavity collector outside? By sending oil through a spiral tube, we are going to transfer that heat to the oil. You understand? Now that oil is, all the heat is absorbed to the oil. Now that heat absorbed oil, we are going to place in a different place. Right? This idea is clear, answer. This idea. The idea is very clear, answer. This idea is very clear. This idea is very clear. Right. Okay. Then they are telling, okay. Right. Okay. Aperture diameter is 20 meter. Intensity of the solar flux striking the Earth's surface is 1000 watts per meter square. Simply calculate the rate at which solar energy is incident on the parabolic disk. The same story. Calculate the rate at which solar energy. Rate at which energy? Rate energy. Rate at which solar energy means rate energy. Rate energy means they are asking the power. Because when something involves with the rate, remember, they are asking what? Energy over time. When something involves with the rate means it links with the time. Energy over time. They are asking the power. They are asking simply calculate the power of solar energy incident on the parabolic disk. So we know the aperture diameter is 20 meter. I told you aperture is a kind of circular area. If you consider the aperture, that is in a circular area. There is a circular area. So you can say simply means you can write down simply as what? Aperture area means we know that. Aperture area means we know that. What is the equation to find the circular surface area? We know that is pi r square. Pi r square. Then pi value, I think they are asking us to consider pi as 3. Then you can find the aperture circular surface area. 3, diameter is how much? 10, 20. Then the radius is 10. Then 10 square. Then the total aperture area is 300 meters square. Now they have given the power. They have given the what? They have given the intensity. They have given intensity what? That when you consider 1 meter squared of when you consider 1 meter squared of area, see, when you consider 1 meter squared of area, the incident solar power is they have given us 1000 watts. When you consider 1 meter squared of area, incident solar power is 1000 watts. Incident solar power is 1000 watt. But they are asking the question, calculate the total solar power incident on the disk. Then you can tell that. You can say that when you consider, now you can substitute the equation also. If not, you can tell 1 meter squared area solar power is how much? 1000 watts. Then when you consider 300 meters squared of area, the solar power is let's say capital P something. The solar power is capital P. Then you can tell that 300 over 1 is how much? You can tell 300 over 1 is equal to what? Capital P over 1000. Capital P over 1000. Then you can write down capital P as how much? Capital P means solar power. The solar power incident on this character is how much? That is 3 into 10 to the power 5 watts. This is one way. If not, you can use the equation also. You can use the equation. Intensity means we can remember. Intensity means we know the power over area. Intensity means we know the power over area. Power over area. Intensity means how much? 1000. Intensity is 1000. You want to find the solar power. Area is 300. So then also you get the same answer. Right? So normally better you use this equation. For you to understand only, I have discussed this idea. 300 into 1000. Okay. Idea is clear answer. First one is clear answer. Clear the first one. First one is clear. Right. First one is clear. Then right. Okay. Okay. Then right. Then simple B. Right. Right. Simple B, they are asking what? The simple B, they are asking. Okay. Assuming that sunshine is available, it's very simple now. Okay, we can do the stories. Okay. Right. Give me 1 minute. Right. Okay, look here. So then we will stop for today. Okay. So then tomorrow also we are now with the pending questions. We'll do the next day. Tomorrow also we'll do a session. Likewise, we'll do sessions. Okay. Then today we'll stop from here. Then next day we'll continue. Okay. So then we'll stop for today. Okay. See you. Bye.